For the last lecture of this week, we're going to look at whatever we've seen from a very different perspective of the human visual system. So we saw that processing images can be done to achieve several tasks such as extract edges, extract blobs, corners, key points, extract representations around key points, segment images, so on and so forth. For many decades, these were used extensively in computer vision applications. In particular, one of the topics that we covered in the lectures, which was a bank of filters using a Gabor filter bank or steerable filters, was about using multiple different filters in different orientations and scales to extract content out of images. To some extent, we'll see now how this approach is similar to how the human visual system processes images. It's not exactly an imitation, but there are similarities in how these methods were used to process images versus how things happen in the human visual system. So to complete that, let's look at a slightly detailed view of the human visual system. To start with, an acknowledgement. Most of this lecture's slides are taken from Professor Rajesh Rao's slides at University of Washington. So unless stated explicitly, the image sources are also the same. So the human visual system can be summarized in this diagram. There's a lot more detail than what you see in this diagram here. But what you see here is the eye and the retina, and the scene around you is here around the human, and the left visual field and the right visual field fall on both the eyes. And then you can see that the right eye goes to the left part of the brain, which is drawn in the blue color here, and similarly the input to the left eye goes to the right part of the brain, drawn in red color here. The primary visual cortex is located at the back, and there are other components that the human visual system passes through, such as the pulvinar nucleus, LGN or the lateral geniculate nucleus, superior colliculus, optic radiation, so on and so forth. So if you observe carefully here, among all the inputs that come in through the retina, most of it go to the visual cortex, but there's a slight deviation of some content here which goes into the superior colliculus. And the superior colliculus is what is responsible for feedback to moving the eye. So the superior colliculus is what perhaps tells you to move your eyeballs to see something, to get a better understanding, so on and so forth, while the visual cortex is what gives us understanding and perception of the scene around us itself. Let's see this in a bit more detail. To start, once again, we talked about this in an earlier lecture too, that the light visible to the human eye is restricted to one part of the electromagnetic spectrum, which goes from somewhere roughly between, say, a little less than 400 nanometers to a little over 700 nanometers, going from violet to red. Obviously, the radiations that you have to the left of violet are called ultraviolet, and the radiations that you have to the right of red are called infrared. So this is known to us. So if you ask us, why is it that our eye receives only this light spectrum the most? It seems to be that as we have evolved, our vision appears to be optimized for receiving the most abundant spectral radiance of our star, the sun. So in this particular case, in this graph on top, you see the energy of the various components in the electromagnetic spectrum. You can see that the sun's energy peaks in the visible spectrum and then falls off over the rest of the electromagnetic radiation. And so that is potentially a reason for why our eyes seem to have got used to that spectrum as the most useful spectrum from a vision perspective. So the retina itself, which is the sensor of our human visual pathway, consists of photoreceptors and also does a lot of image filtering before it passes on information to the next phase of the human visual pathway. So if this was our retina and light fell from left to right here, so the back of the retina is blown up on the right side, so you can see that a bit more closer. So at the far end, it consists of course, epithelial cells, and just before the epithelial cells, the retina consists of what are known as rods and cones, which you may have heard of. But before the photons fall on the rods and cones, there are many other cells too, such as what are known as ganglions, bipolar cells, so on and so forth, which the information passes through before reaching the rods and cones. So each of the rods and cones have specific properties. The rods are sensitive to intensity but not color. And why are they called rods and cones? Their shape, as you can see here, the rods are shaped like this and the cones are shaped conically. So the rods are sensitive to intensity but are not sensitive to color. So they in some sense get a blurred image of what is happening around us. And cones are sensitive to color. They form sharp images and require many more photons to absorb the information. Cones typically form three different types in humans. Each of these cones are sensitive to specific wavelengths. And what are these wavelengths? So you have a set of cones that respond very well to blue color, a set of cones that respond very well to green color, a set of cones that respond very well to red color. Clearly, rods are somewhere in between, where they are not color sensitive but just are sensitive to the intensity of the photons falling on the retina. This should also explain the RGB aspect of color that we choose, because that seems to be where our cones are peaking in the Vibgyor spectrum. So this also explains why a person could be colorblind. So for example, if a person does not have green cones, the person may not be able to say green color in the world around us. So before the photons reach the rods and cones, there are what are known as ganglion cells or other cells in the retina, which typically operate in what is known as an excitatory manner or an inhibitory manner. So in this diagram that you see on the slide, plus denotes an excitatory reaction and minus denotes an inhibitive reaction. So cells are organized this way, where there is a central cell which gets excited when a photon falls on it, and there are a set of cells around it that get suppressed when the photon falls on it. So what happens? Remember, at the end of the day, we will see this as we go through this lecture, that even the eye acts as image filters, and that's the reason we are talking about it now. Having discussed image filters, edges, features, so on and so forth, it's perhaps the right time to be able to relate what we've discussed so far to how things happen in the human visual system. One key difference between whatever we have studied so far to what we are going to talk about in the human visual system is that the human visual system does spatio-temporal filtering. It's not only spatial filters, which is largely what we've seen so far in this course, but it also does filtering over time. We'll talk about this a bit more detail in the next few slides. Before we go there, as we were saying, arrangements of cells in the retina have components of excitatory and inhibitory elements to them. So there could be an excitatory cell flanked by inhibitory cells on either side. So when a spot of light shines on that, when a photon or the spot of light shines on the central cell, so when the light is on, you can see here, these are just a set of impulses. Remember that at the end of the day, the human brain or these cells release chemicals or spikes of electricity, as you can see, which are known as action potentials. So each of this is a spike, and then when the light is turned on, there seems to be an excitatory reaction because the light is at the excitatory part. Those photons follow the excitatory part of the cell. On the other hand, if the light is on and that part falls on the inhibitory part of the cells, you actually see that there's no response or spikes from the cells, because those cells which are inhibitory, even when photons fall on them, they actually suppress and do not throw out any potential. This idea of inhibitive and excitatory is extremely key to how our human visual system works. So there are two kinds. The earlier kind is where we saw the excitatory to be in the middle. So it's called on center of surround cell. You also have the converse, where you have an off center and an on surround cell, in which case you have an inhibitory cell in the middle and then an excitatory around it, flanked on either side. In this case, when the photon or the light is on and the photon falls on the middle cell, your action potentials or your spikes stop for some time. So this particular set of spikes are spikes that you get over time. So whenever so the light was on for that duration that you see there. So that graph is a graph over time going from left to right. So when the light was on, you can see that there is no spike that comes out of that particular cells. Whereas in this case, when the light is in the region outside the inhibitory cell, those are the excitatory cells, and you can actually see that they throw out a bunch of different spikes. So this idea of off-center and on-center, where there are cells that inhibit and cells that excite, are important components of how our visual system works. As I just mentioned, the human visual system is a spatio-temporal filter. So there's a filter on the spatial side which largely resembles a blob detector or a Laplacian of Gaussian for a large extent. So it could be either way. So you could have a Laplacian of Gaussian, remember, the other way, which can peak in the other direction. So you could look at, for a large part, they seem to resemble the Laplacian of Gaussians. But as I was just mentioning, there is also a temporal filter which acts something like this graph here. What does this graph mean? When the light is highest, you get the highest response. After that, you actually get a negative response before stabilizing. Which means, remember again, that in a human visual system, it's a spatio-temporal filter. So when you have a photon that shines, or you have an edge that falls on you, you're first going to detect the edge. Then for a small few milliseconds, the reaction is going to be the opposite in terms of time. And then you revert back to a stable state. So that's what the temporal filter does. Where can you see it taking effect? Why do you think this happens? Here is an example for that. If you've seen this optical illusion, which is a common one, what do you think you see at the center? Black dots are the intersections. Black dots or white dots. This should explain to you what's happening in the eye. So if you see a white dot, when you move your eye from that, remember the response over time is to go back to the other side and make it look like a black dot before you recover and find out it's a white dot. And that's the reason such an illusion happens, is because of how the temporal filter in the human visual system works. Another effect that you may have seen popularly is in what is known as color operant processing. So in this particular case, if you see a lot of these examples, these are also visual illusions, optical illusions, but you may have seen this in many other settings. When you focus on some very strong colors, you typically have a negative after image. So you focus on the yellow and quickly move around, you may find that to be a blue color, and you get a negative after image, which again corresponds to the temporal filter that we're talking about, where you get an opposite response over time before stabilizing to to an equilibrium. As we mentioned, in the human visual system pathway, you also have a component called LGN, which lies somewhere in between. LGN also has very similar center surround and on-off structure to the cells in that particular region, which means there are a set of cells. While one cell could be inhibitory, it may be surrounded by excitatory cells and the vice versa in that same region. So you have combinations of both kinds of cells which together lead to perception the way we see things. Originally, the LGN, or the lateral geniculate nucleus, was considered to be more a relay system that takes the input from the retina and passes it to the visual cortex, but it's now understood to receive a lot of feedback from various parts of the brain, which also come back into the LGN to make it get a more holistic picture of the scene. So there are other feedback that come in to make it get the perception that it actually sees. So the visual cortex, or the V1 cortex, lies at the far end, and let's talk about the visual pathway a bit more detail in the next few slides. In the visual cortex, the V1 cortex, we go back and recall the history of computer vision that we talked about last week, where we said that there were two researchers, Hubel and Wiesel, who were the first to characterize the V1 receptor fields by recording from a cat viewing stimuli from a screen. We also talked about them receiving the Nobel Prize in 1981 for this work. And one of their largest contributions was to show that the V1 cortex has two kinds of cells: simple cells that simply detect oriented bars and edges. For example, you can see a bar detector. A bar is simply a white region flanked by two black regions or otherwise. And an edge detector is the edge detector that we already know. Those are simple cells. While complex cells may be invariant to position, but they are sensitive to orientation. So if you have certain orientations of edges, the complex cells are what pick up those kinds of orientations in their structure. The cortical cells actually end up computing derivatives. Remember again that spatial derivative is orientation sensitive. So you get, depending on how you place your filter, you're going to detect different orientations of edges in your image. So if you had such an edge in your in the scene that fell on your eyes, the spatial receptor field would look something like this, which is a derivative in space, and the derivative in time, as we already said, would peak and then fall off to the other extreme and then gradually go further. To some extent, the spatial derivative and the temporal derivative look similar, but just the the time derivative or the temporal derivative leads to illusions based on time when we are looking at an image. So also, some of these cortical cells have direction selectivity. As we said, the complex cells respond to specific orientations, and the orientated derivative can actually be in an xt space rather than just an x space. So for example, with all the edge detectors that we saw so far, we saw that you could have an edge detector that detects a vertical edge, an edge detector that detects an horizontal edge, or an edge detector that detects an edge with a certain orientation. But because the brain is processing information in 3 dimensions, x, y, and t, you could also have an edge that's moving. For example, you could have a vertical edge that's actually moving. That's what you see here. So you have a rightward moving edge, but as you keep moving the edge from left to right, you now have a cuboid of space x and y and time t, and you would notice that because over time the edge is moving from left to right. Remember again that unlike the simple cases that we saw so far with filters and masks, the human visual system is responding to stimuli that change over time. It's not a still image, but a changing image. So the human eye has to adapt to those changes in the image too. So then it appears that over t, you're going to have an edge in a different direction, because the edge is actually moving from one part of the image to the other part of the image. So in xt dimension, this particular cortical cell will end up having an edge along this direction. So where t comes from the movement in one direction, and x edge is the edge that it actually is. Remember, this is a vertical edge, so you're going to have change along the x direction, and you'll have change along the t direction because it's also moving edge. So an oriented derivative now need not be just in xy space, which is what we've seen so far, but it can be in xt space, yt space, so on and so forth. So remember that the concept of an oriented edge detector is very different in the human visual system because of the concept of time. Why is oriented filters important? So even from a human visual system perspective, people have shown that given natural images, and let's say we had to learn independent filters whose linear combination would best represent natural images, it can be shown that the optimal set of such filters are actually oriented filters and are localized to different regions of the image. Another way of saying this is a natural image simply becomes a positive response to a filter bank with several orientations, and each of these filters placed at different regions in the image. This should perhaps connect you to the discussion that we had with filter banks and Gabor wavelets and Gabor filters and steerable filters, so on and so forth. So even at that time we mentioned that Gabor filters are known to be a little similar to how the visual system, human visual system performs, and this should perhaps give you the context of why we made that statement. Also, at the visual cortex, the final processing also has two pathways called the dorsal and ventral pathways in the visual cortex. So the dorsal pathway is responsible for where information, so which part of the scene in front of you are you seeing what you're seeing, and the ventral pathway corresponds to the what information or what object are you seeing in front of you. So each of these paths lead to different aspects of perception that we see in the scene around us. So the what pathway, is what you see here. The what pathway goes from the V1 cortex to the V2 cortex to the V4 cortex to a couple of regions called the TEO and TE. We are not going to get into this today. There are going to be references at the end of this lecture if you'd like to know more about this. But those are different parts of the brain, as you can see here, which finally lead to understanding what the object is. And as you go from each of these regions, as you go from the V1 cortex to the V2 cortex to the V4 cortex to TEO and TE, each region captures higher abstractions of the information around us. Remember again that if rods and cones and other early processing in the human visual system are only responding to edges and textures, there has to be later layers in the human visual system that make us understand the scene around us, maybe a table, a desk, a wall, a water bottle, so on and so forth. So the V4 gets higher levels of abstraction, the TEO gets even higher levels of abstraction, and this is put together as you go deeper and deeper. On the other hand, the where pathway, you go from V1 to V2 to regions called MST, MT, and what is known as the posterior parietal cortex. So these cells respond to more and more complex forms of motion and spatial relationships, and that's where the where pathway comes into the picture, while the what pathway takes different features and puts them at higher levels of abstraction. The where pathway responds to more complex forms of motion and spatial relationships. So in fact, it is shown that if there is damage to the right parietal cortex, it could lead to a condition called spatial hemi-neglect, where a patient, which is considered a disability, where a patient cannot see one side of themselves all the time. So once again, that relates to the where pathway. So if one part of the parietal cortex is damaged, they really cannot see one side of the scene around them, and the patient behaves as if that left field does not exist at all. So there have been some experiments that have been conducted where people have asked. So these are eye movements that were tracked on the screen, and you can see that the patient is only focusing on the right part of the screen. Or in another case where a patient is asked to draw a clock, the patient ends up drawing only the right side of the clock and does not draw the left side of the clock. These are ways in which this condition is diagnosed, and the condition is known as spatial hemi-neglect or hemispatial neglect. So to summarize the visual processing hierarchy, so you go from the retina to the LGN to the V1 cortex, and from the V1 cortex there are two pathways, the where pathway and the what pathway, where the what pathway goes from V1 to V2 to V4, where V1 gives you a certain set of attributes in your image, low-level attributes in your image. V2 puts things together and gets things like edges, borders, colors, and so on and so forth. V4 gets angles, curvatures, kinetic contours, motion, and so on and so forth. Then TEO gets simple shapes, and TE gets the complex body parts, or perceives the world around us as we see it. In the where pathway, you go from V1 to V2 to MT, which detects things like spatial frequency, temporal frequency, local and global motion, so on and so forth. MST gets even higher levels of abstraction in terms of movements such as contractions, rotations, translation, optical flow, so on and so forth. And finally, you have a multimodal integration and a better understanding of the where pathway and the parietal regions. This was primarily intended to give you a parallel between what we've been discussing so far and how the human visual system perceives. If you're further interested, there's a nice summary of whatever we've discussed so far in the lecture notes of Dr. Aditi Majumdar at UCI on visual perception. And if you're further interested, there are many more links on this slide which you can read to understand more. And the lectures of Dr. Rajesh Rao, from whom these slides were borrowed, is also there as one of these links if you want to read more. Here are some references for you to read.